Hey guys, this is Nuruluda and I am a verified educator at an academy, which is an online learning platform, and you can access my videos over there as well. So those lessons are totally dedicated for your CSI net preparation. So if you are preparing for the exam, you can follow me over there by downloading this app from your app store, and you have to search for my name, that is Nuruluda, and you can find me over there and follow me. Okay, and also you can go to my profile directly from the link given in the description. The benefit of this app is that you can get new courses, dedicated lessons. You can also download the slides from there, and you can watch my lessons offline. So that's all for this, and let's continue with the video.
Hey guys, hello everyone, and welcome to the channel. Now this is the most requested topic which I'm going to cover today, that is Mossbauer spectroscopy, right? So in this video I'm just going to explain you all the things required to understand this Mossbauer spectroscopy, all the terms, everything related to it, like your quadruple splitting, then your Z-man effect, everything whichever is covered, like whichever it comes under this topic, I'm going to explain all of these things. So this is going to be one of the most important video before your CSI net exam. Now before starting this video, I'll just want to request you, if you are new to this channel, if you haven't subscribed the channel, please subscribe it and like this video, so that whenever I upload a new video, whenever I upload a new new video, you will get notification for that. Okay, now let's start with this Mossbauer spectroscopy. So the basic things about it is that this is a gamma ray spectroscopy, right? And here the transition is done between your ground state and excited state of your nucleus. Now the next thing is that the Mossbauer active nucleus, that which nucleus will be called Mossbauer active. So those who are having I value greater than 0, and which have different I values in ground state and excited state. So these are the basic things about Mossbauer spectroscopy. Now let's talk about the principle behind it. What is the principle behind this Mossbauer spectroscopy? So the principle involves that you have a radioactive nucleus like this. Let's say we have a nucleus X having atomic number Z and atomic mass of A. Now when it captures an electron, when it does electron capture, its atomic number reduces and it get converts into another nucleus, right? So these are the basic things which you have read in your nuclear chemistry. So this like this atom or this element X gets converted into Y with atomic number less than 1 unit from it. Okay, now if you do the same thing with this cobalt, so cobalt is having atomic number of 27 and atomic mass of 57. If you do electron capture with it, so electron capture is done from the K shell. Now if the electron capture is done, so it will get converted into iron. So iron 26 and 57, so this iron will be in excited state. So that means so this iron will be in excited state, and when this will try to come into the ground state, that will emit a gamma ray. So that gamma ray, this process is called gamma ray fluorescence, because this iron has been found by this electron capture. This will be in excited state, it will try to come in ground state emitting gamma ray, and that is called your gamma ray fluorescence. So this will act as this whole up to here, it will act as a source. Now this gamma ray which is now emitted by this iron atom, it will go to strike the other iron, like this is happening within the nucleus, right? So now this will go and strike the other nucleus of other iron atom, and that nucleus will now transit from your ground state to excited state. Now this is what we call gamma ray resonance. Now this happens with the nucleus in for which we want to get the information. So this will happen like see, this is the source. Up till here we have source. Now this is for the sample. Usually we take the same atom like we take for iron only. So when this gamma ray will go and strike this iron atom, that will transit from ground state to excited state, absorbing this gamma ray. Now there are certain conditions, there are many things which you have to deal with when these gamma rays are like they are absorbed, and that's all I will explain you in this particular video. So we get signal when this transition will happen, then only we will get signal, otherwise we will not get any signal. Okay, now this happens with the nucleus, we want to get information, and this process is called gamma ray resonance. So two processes are involved, one is gamma ray fluorescence, and where this gamma ray will be emitted, and other is gamma ray resonance, when this gamma ray will be absorbed and resonance will take place between ground state and excited state, right? Now there is a concept of recoil energy. Now what is this recoil energy? See, when this gamma ray strikes the sample, what will happen? the energy of this gamma ray will be that will be utilized in two ways. One will be like for making transition, and other will be to overcome the resonance energy. So sorry, to overcome the recoil energy. Now what this recoil energy is? So whenever this transition will take place, some amount of your nucleus will be pushed backward because something is moving in the like forward direction. So you know what recoil is, right? So some of the part of nucleus will move backward, and that is what we call recoil. So that amount of energy which is like wasted, or you would say that the energy which is required for recoil, that is what we call recoil energy. And the gamma ray which is coming over here, which is making this transition happen, that is gamma ray resonance, that will only fulfill both of the energy, that is to make the resonance as well as to overcome the recoil energy. So we need gamma ray of slightly higher energy than the resonance energy to overcome recoil energy, because if we have, let's say we have this resonance energy of 10 joule, and if this gamma ray is also of 10 joule, then it will come and it will strike, but the transition will not happen because some amount of that 10 joule is now used in your in your recoil also. So let's say if recoil energy is 2 joules, so 2 joule will be required for recoil, and other 8 joule will only be available for transition, and then transition will not take place. So that's why we need a gamma ray of slightly higher energy, let's say 12 joule for this case. I've just taken it as a case. So if I have taken 12 joule energy of this gamma ray, then what will happen, 10 joule of it will be required, that will be utilized for making transition, and other 2 joule will be overcome, like other 2 joule will be utilized in overcoming this recoil energy. Now the formula for this recoil energy is given by this, that is Er is equals to E square upon 2 mc square, where m is the mass of nucleus, c is the velocity of light, and E is the energy between energy state, excited state and ground state. Now if mass is more, if the mass is higher, then the recoil energy will be less. So that's why we take a particular nucleus which is slightly higher in mass for Mossbauer spectroscopy basically, and that should be bound, like that should not move. So that's what this point suggests, that the recoil energy can be minimized if we bound the nucleus very strongly. So how we can bound the nucleus very strongly? By keeping it in a crystalline solid. So that's what the Mossbauer effect says, that if you can minimize the recoil energy and if you can make it equal to zero, at that time what the effect you will see, that how much gamma energy will come, that will be only utilized in making the transition, that will be only utilized in making the resonance, and at that time it is called Mossbauer effect. And that's what Mossbauer recorded it. And right, so this by like how we can minimize this recoil energy is that by bounding the nucleus strongly, and that can be done by bounding it inside a crystalline solid. If the nucleus is put inside a crystalline solid, at that time it cannot recoil, the whole of the energy will be emitted, and that energy will be utilized for making transition from ground state to excited state, and that's what your Mossbauer effect is. So this is important thing to remember. Now let's talk about few other important things. Alright, so now let's talk about that how we record Mossbauer spectra, right? So as I told you that this is that cobalt 57 act as a source, and it captures an electron from the K shell to convert it into excited state iron atom. And over here the gamma ray fluorescence occurs, and then that makes gamma ray resonance to happen. Now if this gamma ray fluorescence has 10 joule of energy, then obviously we need, like for to overcome the recoil energy, we need 10 plus 2, that is 12 joule of energy, right? So to increase the gamma ray energy from 10 joule to 12 joule, what we can do is that we can move this source towards this sample, right? So if we move this source towards this sample, this energy can be increased. And this energy over here I am just showing in joule, but the energy will be expressed in in the form of frequency. Okay, so in the Mossbauer spectra we express it in the form of frequency. So for that I'll just tell you after that what this Doppler shift is. So for the transition in sample, the source can be moved towards the sample or away, depends upon what we need. If we need to increase the energy or decrease the energy, that depends that whether you want to move the sample towards the source, you move the source towards the sample or away from the sample. Now speed at which the transition occurs is called the chemical shift. Now I have drawn a table over here to show you guys that see, I have just taken energy in the form of joule, and it's just a hypothetical way just to explain you. Okay, So let's say we are moving this source, we are not moving this source earlier, and the energy is 10 joule. And remember that 12 joule energy is required for the transition to happen. So initially the intensity of gamma ray which you will get is 100%. That means no gamma ray is getting absorbed. All the gamma ray is getting like you are not absorbing any of the, like the sample is not absorbing any of the gamma ray. Now if you increase slowly the speed of your source, then the energy of gamma ray will also increase gradually, and when this energy comes out to be the energy which is required for your transition to happen, that is 12 joule, then the intensity of this gamma ray decreases. That means the 70% of gamma ray is now absorbed. So this is how over here you are going to get the signal, and this signal will look something like this. See, over here the intensity is 100%, but as the speed is slowly increasing, the intensity has now decreased at this point, at which the speed at which the transition has occurred. Now this is what we call Doppler shift, because we are moving the source with respect to sample, and that will increase the frequency. The energy, as I told you, the energy is expressed in form of frequency. So I'll talk about frequency over here. So the increase in frequency, or the change in frequency, when you move the source or sample away or towards each other, that is given by this formula, that is delta mu is equals to delta nu is equals to nu v by c, where nu is the frequency of your source, v is the velocity at which it is moving, and c is the velocity of light. So if you'll put over here, you will get that how much increase or decrease in the frequency you are getting. Okay, so this is what Doppler shift is, and numerical has been asked once or twice based on this formula. So this concept, like this was the concept behind it, this is the formula which is required to solve it. Now let's talk about the number of signals in Mossbauer spectra. So the number of signal depends on three things. First of all, see, I told you that for iron atom, it's Mossbauer active, and in ground state it is having I value of half, and in excited state it is having I value of 3 by 2. Right? Now what will happen? See, it can have like the electric field gradient. What is this electric field gradient? Electric field gradient means the electric field or the electric charge on this atom, if it is in this nucleus, if it is like symmetrically distributed, if electric field gradient is symmetrical, that is equals to 0, then you will get 0 electric quadrupole. That means in like there will be no splitting which will happen over here. But if your electric field gradient is not equal to 0, if it is asymmetrically let's say distributed, then the electric quadrupole will not be equal to 0, and at that time splitting will happen. Now in how many type the splitting will take place, or in how many number this splitting will take place, that is given by this formula, that is number of electric quadrupolar moment, or the number of splitting, is equals to I plus half. Okay. So when we talk about ground state, in the ground state this electric field gradient is equals to 0, and over here no splitting will take place. So this I is equals to half will be stay like that only. So I have just written it out over here, but make like you pay focus over here what I am drawing right now. So I will be is equals to half. Okay, it can be plus or minus half, both at one place only. So this is degenerate energy level. Now for excited state, electric field gradient is not equal to 0, and at that time electric quadrupole splitting will take place, and that will be equals to I plus half. And we know that I value for excited state is 3 by 2. So 3 by 2 and plus half will give you how much? It will give you 2. So that means it will split into two levels, 1 and 2. One will be having 1 by 2 energy level, and other will be having 3 by 2 energy level. So these two are degenerate. I have drawn separately over here, but they are degenerate, means both of them are having same energy. So how many transition are possible here? So one transition will take place from here. So the selection rule for transition is that your delta should be either 0 or plus minus 1. So if it transits from here to here, the I value will be equal to 0. So one transition is possible here, and one more transition is possible when this will transit from here to here. That means over here your I value will be plus minus 1. So that means two peaks or two transitions are taking place for this. So you are going to get two signals in your iron atom, right? So this is the case in the when you have electric quadrupolar moment. Now when this electric field gradient will be 0 and when it will not be 0, this I will explain now. Right, so let's now understand that when this electric field gradient will be equal to 0, that is when your charge distribution will be symmetric. So when your there are two cases, right? First one is your electronic symmetry, and other one is your ligand symmetry. So electronic symmetry will be attained if your T2G is having 0, 3 or 6. That is either it is completely unfilled, half filled or fully filled, or EG is like completely unfilled, half filled or full filled. Okay, so 0, 2 or 4 electrons in that. Then these are the condition for electronic symmetry. Similarly, ligand symmetry will be there when you have all ligands of same kind, that is all the ligands are same and they are present at equal distances from the metal. So these are the two conditions which will give you symmetric charge distribution. So if both of the above conditions are fulfilled, then electric field gradient will be equal to 0, right? So if your electric field gradient is not equal to 0, if it is not equal to 0, then the electric field gradient will interact with the like your electric quadrupole of the quadrupolar nuclei, and due to this the degenerate energy level is split into I plus half. If your energy level for I values, if you are having I values like half, 3 by 2 or 5 by 2, then the number of splitting will be attained by this formula, that is I plus half. And if your formula is like 1 2, like if you have I values like 1 2 3 4 5 like that, then the formula used to find out the number of splitting will be I plus 1. So this formula will give you the number of splitting which will be done in case of when your electric field gradient will be not equal to 0, that is if ligand symmetry and electronic symmetries are not fulfilled. So in both of these cases, your energy levels will split in these number of lines further, and this is called electric quadrupole splitting. So this is also one of the important point where this decides that how many signals or how many peaks we will get. So I have taken one example over here. So let's take an example of this complex, that is FeCN6 4 minus. Over here, if you can see that Fe like iron is having D6 electronic configuration, and it is low spin due to due to strong field ligand present over here. So the electronic configuration is T2G6 and EG0. So electric symmetry is obtained here. So it is electronically symmetric, and ligand symmetry will be like it is also present because all the ligands are of same kind and they are attained with the metal, and ligand metal and distances are same. So that's why electric field gradient will be equal to 0. So no splitting will take place. So in the ground state, where I was showing you with two lines, here you will be having just one line, and over here also for excited state, here also it will not split, it will be just a single line. So how many peaks you are going to get, how many transition you are going to get? So that now like the selection rule is same only, that is delta I should be either 0 or plus minus 1. So for case of this, you can have like your delta I is equals to 1, and how many peaks you are going to get? You are just going to get one peak. So if your electric field gradient is not equal to 0, that I discussed in the last, like when I was discussing about your number of signals in Mossbauer spectra, there I told you that there were two peaks. There also I took the same example of iron, but there splitting was there. Okay, and there I took where your electric field gradient was not equal to 0. But if electric field gradient is equals to 0, which is this case, then you are just going to get one peak. So these are the cases for iron atom where you will get different types of peaks depending upon the electric field gradient. All right. So there are certain more condition. Let's say if we have electronic symmetry, that is your electric field gradient is like approximately equal to 0. Okay, it's not equal to 0, but it's approximately equal to 0, and ligands are asymmetrically filled. At that time, what will happen? Since ligand is unsymmetrically filled, so I excited state of I will split into 2 depending upon that formula, that is I plus half, and since I value is 3 by 2, so 3 by 2 plus half will give you 2. So it will split into two lines, and these two will be degenerate. Okay, just mind it, I have just drawn two lines over here, but that doesn't mean these two are different. These two are of same energy level, they are degenerate. So how many transitions are possible? Either delta is equals to 0, that is from half to half, or delta I should be 1, so that means half to 3 by 2. So two transition are possible, two peaks are possible, but this gap is very less. Why this gap is less? Because electric field gradient is approximately equal to 0 and ligand is unsymmetric, so that's why splitting is there, but the gap is less because electric field is equals to, because electronic symmetry is obtained. Okay, so in this case, since the gap is less, you are going to get a broad peak. Instead of getting two peaks, you are going to get a broad peak. So this is an example where you will get broad peak. Now let's say that if a strong sigma donor and pi acceptor ligand like your CO, NO, all these are used, or all these are present, then what will happen? They will pull electron to one of the direction. Okay, so in the metal, they will pull electron towards a particular direction, and that will cause like a very like then the like as I told you that electrically the charges will not be present in a uniform manner, so they will not be like symmetrically arranged. Now they will be dearranged, okay, or they will be unsymmetrically arranged due to the pull effect of or the electron pull by this sigma donor and pi acceptor ligands. So in that case electric field gradient will be way more than zero, that will be very high, and in that case you will be having this I value will split into two, and over here you will get two peaks. So these two peaks are got just because of your strong sigma donor and pi acceptor ligands, right? So these are certain cases, certain different cases in which you will get different types of peaks. Now I have taken an example over here to show you the effect of this. So let's say we have this FeH2O5Cl plus and FeH2O5Cl2 plus. So in this case iron will be in, if you find out the electronic configuration, so iron will be in D6 electronic state, and over here iron is in D5, right? And these are weak field ligands, so this will be high spin, and the electronic configuration will be how much? It will be T2G4 and Eg2, right? And over here it will be like T2G3 and Eg2. So this is electronically asymmetrically filled, and ligand is also asymmetrically filled. So both of the cases are not fulfilled. Both of the cases for electric field gradient are not fulfilled. So that's why splitting will be done into two, and the peaks will be very, like the difference in the peaks will be high. Okay, so the peaks will be away from each other. And over here, since it is electronically symmetry, but ligand is asymmetrically filled, so that's why what you are going to get is this, that the peaks will be formed, two peaks will be formed, but the distance between these two peaks will be less. So these are the conditions which depends, which cause your splitting, and these are the cases where you will see that how the chemical shift will change. Okay, so based on this there are certain more things to be discussed. So the next one is called hyperfine splitting or Z-man effect. So what happens, see, till now I was drawing these two lines and these four lines together, and I was showing that these all are degenerate. But now what will happen if you apply external magnetic field? So in external magnetic field, these two were degenerate till now, but in external magnetic field they will also split into two, and these four also split into four different energy levels. So now what will happen, now in case of external magnetic field you will see a, like how many transition you can see from this plus half to 3 plus 3 by 2, one transition will be there. From here to here, two transition. From here to here, three transition. Similarly from here to from 1 by 2 to here also you can see that how many transitions will be there, total of 6 transitions will be there, right? So these 6 transitions will be shown like this. So the intensity of these 6 transitions will be in this ratio, that is 3 ratio 2 ratio 1 ratio 1 ratio 2 ratio 3. So these intensity ratios depends on the energy difference between these two, right? So see how the transitions will be from plus half to plus 3 by 2, right? Then plus half to plus half, right? And plus half to minus half. Plus half to minus 3 by 2 transition will not take place because now the difference is more than 1, right? Similarly minus half to plus 3 by 2, it will not take place. So minus half to plus half, minus half to minus half, and minus half to minus 3 by 2. So total of 6 transitions will take place, and in this way you will get 6 peaks of this intensity ratio. So this is called hyperfine splitting or your Z-man effect. I'll talk about few formulae also at the later of it. First of all, I'll just explain all the concept and all the important points. Next one is your chemical shift. So this topic also comes under isotropic shift. So like isotropic shift is also one of the example of your chemical shift. So what happens, why this chemical shift value decreases or increases, why it shifts? Okay, so you have to remember few things. I have taken them out and written it out so that you can understand it well. So chemical shift will decrease or chemical shift will reduce. See, this is the table, like this is the way how the chemical shift will be denoted on in this number line, and the chemical shift will decrease if the pi acceptor character of ligand increases, the oxidation state of iron increases, and the electronegativity of negative ion in the anionic compound also decreases. So these are the three conditions. If any of these conditions are present, then chemical shift will decrease. Few examples of it like this. Few examples based on this I have taken. So we have FeBr2, FeCl2, and FeF2. So since you can see the electronegativity of Br is least, So that means if electronegativity decreases, then chemical shift also decreases. So Br will be least, having chemical shift value of least, then FeCl2, then comes FeF2. Now let's talk about the other factor, that is oxidation state. So over here in this K3FeCN6, iron is in +3 oxidation state. Over here in K2FeCN6, now yeah, over here oxidation, the oxidation state of iron is +2, right? So yeah, so oxidation state of iron increases, then chemical shift decreases. So that's why this will be lesser in chemical shift. The next one is if the pi acceptor. So if I take two complexes, we have FeCl2PPH3 whole 4, and I also have FeCl2PMe3 whole 4. So for PPH3, we all know that phenylphosphine, triphenylphosphine has more pi acceptor, pi acceptance. So that's why this will decrease the chemical shift value as compared to trimethylphosphine, right? So these were certain cases which will affect your chemical shift values. All right, so now let's talk about the last and the most important part of explanation, and that is your isomeric shift, okay, or your isomer shift. So that is given by this formula, that is delta is equals to K Re square minus Rg square, and psi s square minus psi s square of your sample minus psi s square of your absorber. Okay, so this is your sample source, and this is absorber, or source and sample. So you can say them like that. So psi x square is nothing but your electron density of your s orbital, right? And Re is the radius of your excited state, and Rg is radius of your ground state. Psi s is nothing but the electron density of your s orbital of your source, and this is electron density of your s orbital of your absorber or the sample. Okay, so this formula gives you the isomer shift. So you don't have to remember this formula, you have to see that what are the application part of it. So for iron, you should know this thing, that the radius of your ground state is more than the excited state. So that means delta R, which is over here, Re square minus Rg square, that will be negative because ground state radius is more than excited state. So your compression will take place over here in iron, and isomer shift will be directly proportional to minus psi s square of sample, sorry, psi s square of your source minus psi s square of your sample or your absorber. So now what it says, that if there is increase in s electron density, then isomer shift will decrease, and if there is increase in d electron density, then d electrons, as you all know, that they will shield the s electrons. So that's why isomer shift will increase. So you just have to remember this thing, that if there is increase in s electron density, then isomer shift will decrease, and if there is increase in d electron density, then isomer shift will also increase. So this is for your iron. So for iron you have to remember, and one more there I am going to give you example, that is for your tin. So for tin, things will be totally opposite of it, because over there expansion takes place, that is excited state radius is more than the ground state. So that's why everything will be opposite of it. That means over there, if you increase the s electron density, then isomer shift will increase, and if you increase the d electron density, then isomer shift will decrease. So you have to remember these few things in order to do questions. Now that's all for the explanation part of it. Now I'll just take few questions so that it will be more clear to you, and you can understand that how to apply all these things which you have read and which you have understood to solve questions, right? So let's take few questions which were asked in CSI previous years of net exams. And this is the first question which was asked in CSI June 2016, and this was asked for 4 marks. And you can see that how simple the question was. The question says that to record Mossbauer spectrum of Fe, that is iron containing sample, a source X is used, right? Now X after nuclear transformation gives Y, which gives gamma radiation used to the Mossbauer spectroscopy. So X and Y respectively are. Now I told in the starting only that for iron containing sample, what we take as a source, we take cobalt 57 as a source, and it does electron capture from the K shell in order to get transformed into iron excited state, right? So we know this thing, that this 57 cobalt, like 27, when it does electron capture, so it does convert into 57 Fe26 star. That means it is in excited state, and then it undergoes, like, then it comes then it does gamma fluorescence, and then gamma radiation is emitted, that is used for Mossbauer spectrum, that is used for gamma resonance. So what will be the correct answer? The correct answer will be option number 3, that is 57 cobalt is like what it does electron capture to get converted into excited state of 57 iron. So see how simple the question is. It was asked for 4 marks. Let's take one more question. All right, so let's take this question which was asked recently in CSIR June 2017, and this question was asked for 4 marks, right? Now the question says that the Mossbauer spectrum of complex Fe110 phenanthroline whole twice NCS twice shows 2 lines at 300 Kelvin, 4 lines at 186 Kelvin, and again 2 lines at 77 Kelvin. Now this can be attributed to, you have 4 options, that is change in coordination mode of NCS, like change in spin state of iron, cis trans isomerization, and change in metal ligand bond distances. Options are given like this: A and B, B and C, A and C, and B and D. Now what is the thing which is given to you? I'll just draw it over here so that it becomes easier to interpret it, right? So we have at 3 different temperatures, we have like this, that is at higher temperature, that means at let's say at 300 Kelvin, we have 2 peaks. So I'm just drawing them like this, right? So why this is so, why I'm drawing so, I'll just explain you. And this is at 300 Kelvin, I'm just drawing this, and the one at 77 Kelvin. So at 77 Kelvin also you are getting 2 peaks, so I'll just draw them near to them. Why? I'll tell you why. Okay, so 77 Kelvin. Now before going into the more detail of this, you have to know this thing, that NCS is an ambidient ligand, so it can bind in 2 ways, that is either in the form of NCS or SCN. Okay, now NCS is a strong field ligand, and in case of SCN it behaves as weak field, right? So in both of the cases, like iron is in +2 oxidation state, so it's D6. So D6 strong field will give you low spin complex. Low spin complex means over here low spin complex, when you will be having low spin complex, at that time it will be having electronic configuration of T2G6 and EG0. Okay, in case of NCS, when it binds like SCN, at that time it will be having electronic configuration, like it will be high spin complex, and that will be like T2G, like T2G4 and EG2. So it will be like that. So it means that over here in like see ligand ligand symmetry is not present. Okay, so that is the basic thing. But due to this that is due to electronic symmetry in this, in case of NCS, the splitting will not be that much. So they will split in 2, but the splitting will be very less. And in the weak field they will split in 2 peaks, but the peaks will be differently. Like I told you that for iron +2, I told you guys that in case of weak field and strong field, how many peaks. So in case of a strong field, I told that there is just 1 peak, but it will split because there is ligand degeneracy, right? So electronic degeneracy is not there, but electronic symmetry is not there, but ligand symmetry is, in case of NCS, electronic symmetry is there, but ligand symmetry is not there. That's why instead of getting a single peak, we'll get 2 peaks over here. That's all what I discussed while explaining about iron strong field and weak field. And at 300 Kelvin also you are getting 2 peaks, but they are separated by two different they are separated at more distances. So these are 2 things are sorted, like at lower and higher temperatures what is going to happen. Now the thing which is so why we are getting 4 lines? So 4 lines you are getting because, see, 4 lines, how you will get 4 lines? They will be something like this. So you will be getting 4 lines something like this. So in between of it you will be getting 4 lines at 186 Kelvin. So due to the the 2 things which can only possible over here is that the change in coordination mode of NCS, that is the first one. And why this is happening? So because change in spin state of our iron is happening, because once it is in strong field and one is in weak field. So once it is in low spin, and another time it is in high spin, so spin state of iron is getting changed. So these 2 effects, A and B, are causing this to happen. Now this 4 peaks cannot be explained based on these 2 things. So it can be predicted, like the answer can be predicted, because these things will not alter this, right? Cis and trans isomerization will not alter, and change in metal to ligand bond distance is also not happening over here. That will happen only in that where John Taylor distortion and all other things are possible. So here nothing is like that. So these two, C and D, are not possible. So the only thing possible is A and B. So the option 1 becomes your correct choice. Now over here, since this is a reasoning type of question, like where you have to give reason for that, so like for these two peaks it's justified, but for four peaks like you cannot justify with these two statements, right? So you can take that as a additional information which is given to you between these two temperatures, but yeah, these two are justified based on these 2 points only. So you don't have to worry about the 4-line distribution, you just can answer it based on this, right? So I hope this is clear to you. So it's just because this NCS can bind in two ways, either in NCS or SCN. In case of NCS, it can bind, it act as a strong field here, and if it is a strong field, so low spin complex will be found. And SCN, if it will bind as SCN, it will be acting as a weak field, so high spin complex will be found. And over here, so that's what it is given, change in coordination mode of NCS. This is the correct option, and since it is changing, so the spin state of iron is also getting changed, low spin to high spin. So that's why these two options are correct option, right? So like this you can easily get 4 marks from here. I'll take one last question for this video. Right, so this is the last question for this video, and this question I don't know in which year it was asked, but it was asked by one of the student on Facebook page. So I'm taking this question so that it's a different kind of question which we did till now. So it's based on numerical. Okay, so I want to include this also so that you can see that how numericals can also be solved based on this Mossbauer spectra, right? So the question says that in Mossbauer spectra, source emitting at 14.4 kilo electron volt, which is equals to 3.48 into 10 to the power 18 hertz. This is given to you. Okay, had to be moved towards absorber at 2.2 millimeter per second for resonance. Now the shift of frequency between source and absorber is, so you have to tell the answer in megahertz. So how to do this question? First of all, you have to use this formula, that is shift in frequency is given by this, that is delta nu is equals to nu into V by C. I gave this formula, I have given you this formula, right? So this formula is based on your Doppler shift. So this is what you have to calculate. So frequency is given to you. Now frequency is given in two things, that is in kilo electron volt and in hertz. You have to use in hertz because you have to calculate the answer in hertz. So it's 3.48 into 10 to the power 18. Now this is in hertz, and velocity you have to keep in like if you are keeping this in millimeter per second, then velocity of like the speed of light you have to keep in millimeter per second. So it's 3 into 10 to the power 8 meter per second. If you will convert it into millimeter per second, that will come out to be 3 into 10 to the power 11 millimeter per second, right? So this value is velocity of light in millimeter per second, and it is already in millimeter per second. So this is how you have to do. And now what you have to do, you have to just solve it out. You have to just multiply and subtract and divide. So you are going to get this, that is 2.55 into 10 to the power 7 hertz. So this is what you got, or you can write it as 25.5 into 10 to the power 6 hertz, right? Now 10 to the power 6 hertz is nothing but your megahertz, so you can write it as 25.5 megahertz. Now the correct option, if you'll check the options, so third option becomes your correct choice, right? So in this way you can do questions based on a Mossbauer spectra. I hope you guys like this video, and if you like this video, give it a like, subscribe to the channel if you are not subscribed yet. And one more thing, if you are preparing for CSIRNet and if you want to prepare more, if you want more topics to study, if you want more questions to practice, you can follow me on an academy. The link is given in the description. I have like 30 courses which are absolutely free. Each courses comprises of like 15 to 10 to 15 videos in that. So if you'll watch all those courses, approximately your 20-30% of your course will be covered from there. And all my videos on YouTube, like they will cover your around, so all my videos on YouTube, if you will add them all, so almost your 60 to 80% course is completed, if I exclude organic chemistry. Okay, from inorganic and physical most of the things are covered. From organic also I have covered pericyclic reactions, Also your basics of organic is covered on Unacademy. So there are lots of stuffs available. So before if you want to like get a revision of the things, if you want to like see the things at one glance, then you can go to my Unacademy profile as well as on YouTube, and you will find lots of videos there, and I hope that you people will like it. Okay, so do tell me in the comment section what you liked and what you not, and if you want to ask anything, you can ask me in the comment section. One more thing, that I have a group, Facebook group. You can join that group as well for discussion. You can join my Facebook page to stay updated with everything. And so yeah, these were all things related to the promotion and everything, right? So thank you so much for watching, and have a great day. Bye bye.